Okay, so we're just starting chapter 24. This is the last chapter of the quantum field theory. And so let me tell you what we're going to do. Well, we know how Wilson thinks about quantum field theory. He thinks about quantum field theory as an effective theory, not a fundamental theory. And he imagines it comes with a physical cutoff. And quantum field theory only gives you a correct description of nature at length scales above the cutoff. It's a particularly beautiful way of thinking about physics. For us, the kinds of things that we have seen is that there's no infinities in Wilson's way of viewing things. Corrections are introduced slowly and systematically. It also explains, so Wilson actually explains why nature uses renormalizable quantum field theories. So that's what we've seen. There are many other things that it does. So for example, phase transitions are described near fixed points of the renormalization group. And one sees a remarkable universality coming up. So different systems have very similar behavior at the phase transition, determined entirely by how many degrees of freedom and what symmetries the systems have. So two systems with completely different microscopic physics will have the same macroscopic physics. So this idea called universality, which plays a big role in phase transitions, for example, is something that we haven't considered at all. So Wilson has this really beautiful conceptual understanding of quantum field theory. At the same time, Wilson's way of computing is not great. It consists of iterating three steps. The first step, we separate out some shell of high momentum modes. The second step, we integrate over these high momentum modes. And as a third step, we then rescale the theory after we've integrated over the high momentum modes. This is nice. It means that you're organizing the theory according to scales. So that's a new conceptual understanding. But step number 2 is very hard. You generate loads of all sorts of terms, and it's actually very hard to carry out that integration occurring in step 2. So I think it's fair to say that Wilson has a beautiful conceptual understanding of quantum field theory, but his calculational scheme is not great. On the other hand, Feynman, Schwing, and Tomonaga have a lovely computational framework. They have the very powerful language of Feynman diagrams. You've seen that the Feynman diagrams have all sorts of nice interpretations. More than that, there's actually an algorithm to calculate the values of Feynman diagrams, to do the integrals of momentum space. And to remind you of what goes into that algorithm, so one of them is Feynman's trick, which allows us to replace products of denominators by sums of denominators. Then we have dimensional regularization, tables of integrals done in dimensional regularization that we can just look up to figure out what the integral over the momentum is. And then finally, we've got the integral over the Feynman parameters, but these are always integrals over some finite range, so they can be handled numerically. So Feynman, Schwing, and Tomonaga have a nice way to compute, but it's a bad conceptual framework. Infinities appear that are ill-defined. You have to define them. Apart from that, if you really think about the loop expansion conceptually, not obvious that what you're doing makes sense. So you've got no insight into why infinities start to appear. So it's just not a very good conceptual understanding of the subject. So what we want to do in this chapter, we want to learn to think like Wilson and calculate like Feynman, Schwing, and Tomonaga. So in that way, we're going to marry the best of both of these two descriptions, and that really is going to lead us to the Kalansa-Manzik equation. Okay, so let's get started. So let's start off, and I want to say, if we speak to Feynman, Schwing, and Tomonaga, so let me just say FST, and we were to ask them what are they doing when they study quantum field theory, they would say, well, you have to study a renormalizable quantum field theory. They wouldn't justify it. They just tell you have to study a renormalizable quantum field theory. That's what nature uses. And they'd say, with a cutoff. So the cutoff will define your infinities with a cutoff lambda, but they would tell you, but you must take lambda to infinity. Okay, this is related to their view that really quantum field theory is a fundamental theory. Let's see what Wilson would say if he saw these computations. How would he describe them? Okay, so Wilson would say the following. He would say, well, since you took the cutoff lambda to infinity, you've actually been flowing for an extremely long time. This has been a very long RG flow. So Wilson would say that we are considering an arbitrarily long RG flow. Okay, so we've been flowing for an extremely long time. So we must have started close to some fixed point in the ultraviolet. And typically you'd assume that you started close to the free field fixed point. So let's just imagine, let's just say we started close to the free field fixed point, and then we flowed. Now, this might look like a bit of an assumption that we started close to the free field fixed point, and it definitely is. Are there interesting questions we can ask when we don't start close to the free field fixed point? Of course, we would love to be able to start in the UV close to some interacting fixed point and study the flow starting from that interacting fixed point. But that's hard to do, and it goes beyond perturbative quantum field theory. So the reason why we're assuming that we've started close to the free field fixed point is that's all we can do with our weak coupling tools. So this is not a statement about what's interesting. It's a statement about how poor we are at calculating. We've only really got perturbative quantum field theory under good control. But anyway, so let's imagine we started close to the free field fixed point. We flowed for an arbitrarily long time. What does that mean? That means that all irrelevant couplings were set to 0 by the flow, because we flowed for so long. Now, by the way, let's just mention one thing, okay? Feynman, Schwing, and Tominaga certainly would not have understood irrelevant coupling. So that's not how they would have said it. So Feynman, Schwing, and Tominaga would not have said irrelevant couplings. They would have said non-renormalizable couplings. That's how they would have said it. So they would have said there's no non-renormalizable terms. Of course, they wouldn't have explained it, but Wilson explains why there's no non-renormalizable terms. They've been set to 0 by this very long flow. Good. Okay. So what does that mean? That means in our low energy theory, and of course, you see, so we flow down to low energy. We've been flowing for an infinitely long time. So we are at low energy. After this extremely long flow in our low energy theory, we only have information about the marginal and relevant couplings. Now, I want you to keep in mind one other thing. When you talk about irrelevant couplings, there's loads of these, an enormous number of these. So there's lots and lots of irrelevant couplings. When you talk about marginal and relevant couplings, actually, there's only a handful of these, very few of these parameters. So what you see is this very long RG flow has gotten rid of a whole lot of data that is completely irrelevant for the low energy theory. We've only kept information about the marginal and relevant couplings, and this is the only data relevant to the low energy physics. So you can start to see why the Feynman, Schwing, and Tominaga description is slightly easier. they've thrown away a lot of data that just isn't needed to describe the very low energy limit of the theory. So we're only left with a handful of parameters, those corresponding to the marginal and relevant couplings. Let me just make one final point, which is that there's the flip side of the coin again. When we say the irrelevant couplings have flowed to zero because they've gotten smaller and smaller and smaller, the flip side of that is we should say all relevant couplings have flowed to be massive. So you'd expect relevant couplings in the low energy theory to be very, very large. And that's not what we observe. Particle masses really are finite. So we need to do a significant amount of fine tuning. So because of that, any effective theories that you have with relevant couplings, these are often called unnatural. Okay? These are often called unnatural. And it's because you need a lot of fine-tuning. You need fine-tuning to get finite relevant couplings after this extremely long RG flow. So it's only in theories that have no relevant couplings that there is a natural low energy effective theory. Okay, good. So we've just taken the normalizable quantum field theories. We've described it the way Feynman, Schwing, and Tominaga would describe it, and we've described it the way that Wilson would describe it. We'll keep going in a moment.